If your internet speed is low, kindly connect to your cells, because that is, I guess, a better option, because we are going online also. Are we guys here? Javed sir? I guess you missed some part, huh? Okay. Kindly follow. If you have any query, just you raise your hand, then I'll stop. I'll clear it. Are we guys yes? Yeah. The sequence which you have copied and saved in your notepad, you can copy that sequence and paste it here. Proceed. So as you can see, there are several setting options here. Okay, this is the main thing. You enter your sequence here. After that, move to general settings. Here you can give so many product size ranges are present here, from 150 to 250, 100 to 300. Okay, when we do gene based sequencing, we generally go for at least a product of almost 1 kb. So I will ask this software to give me the primers of product length of almost 851 to 1000 bases. Okay. You are here. Go to general settings. Reached? Okay. Then product size ranges are there. Okay. According to the requirement you have in your experiment, you can select the product range. Here I have selected for 851 to 1000 bases. As you can see, so many other options are also here. What primer size you want, what TM you want to give for, how much GC content should be there in the primer, everything is here. Shall I proceed? Okay. Then rest of the settings I go with the default thing, and then click pick primers. Okay, following na? Good. just scroll down, you can see how many pair of primers it will give you. It will give you, I guess, 5. Yeah, 5. You will get 5 pair primers for your sequence. Now to select which, okay, taking time. The next thing to look for is what is the length of your primers here. 20 base pair, same for forward as well as your reverse. I guess it is quite clear. Left primer, forward. Reverse primer, right primer as your reverse. Okay. Then what is the next thing you need to notice is the TM. It should not have that much variation. I would consider only 2-degree variation is fine. Okay. Next is your GC content. Okay. It should not be more than 60, I guess. 60, right, sir? 60, yeah. Okay. Now you have 5 set of reverse and forward primer. Now which one to go for? For that, I would like you to open a new tab and enter OligoCal C. You can explain. Are you guys here? Click on OligoCal C, this one.
For primer designing, there are 2-3 things are there. It's very important for the primer designing. This is your length of the primer. That is, it's the ideal length 20 to 20 nucleotide. Second point come, this is your melting temperature. This is one of the most important things for the primer designing. Its ideal range is approx 62, 61 or 58, may be vary, and both primers forward and reverse, that's how the little bit difference, 1 degree or 2 degree difference, not more than that. Third thing is GC content. The ideal range is GC content is 50 to 55. If range is like that, this is the best primer for your region. And once come is the product size. What is your product size here? We are designing the primer here, PCR and qPCR. The difference only is your product range. For qPCR, we are preferred to approx 150 base pair product size, and in normal PCR, we can range it vary from either 150, either it reaches to 800 or 1200 base pair. There is a difference only here. Rest of the thing, Shanu explain why.
Okay, thank you, sir. Now we need to check these sequences whether some complementarity is there, some loop formation is there or not. There are certain parameters to check whether the primers are going to work properly in the cycle or not. Okay, to check these parameters, what we need to do is we are going to use a program known as OligoCal C. Okay, I guess you guys have already opened OligoCal C in your tab. Okay. just copy your forward primer and paste it here. This will give you your reverse complement strand also, as well as it will tell you that what are the physical constants of this sequence. The length, the molecular weight, GC content, everything is here. Now we will go to check self-complementarity. See, there are three parameters here. First is hairpin formation, which is very important, which generally happens. Second is 3' complementarity, and all potential self-annealing sites. These are the three parameters we go for to check the primer we have. And when it is coming all none, you're good to go. Do you want me to repeat? Okay. Copy the sequence from here, paste it in oligocal C, then go for check self-complementarity. That's it. These three parameters are very much important, because if any one of the three things happen, what is the result of that? Your annealing will not happen in the cycler. The primer will not go and bind to that strand. So you need to have none for all these three parameters. Same way, we are going to check for reverse also. So after we have checked, I will show you what happens when you're getting not a good primer. I guess for this we have all the primers good only, so as you guys can see, both forward as well as reverse primers are passing our quality check, so we can proceed with this set to design the primer. Okay, next is what? Outsourcing. You synthesize your primers. Okay, mostly what I have faced, because I can tell I have designed many primers, what I have faced is when you have some problems with the primers, none of them are going well for your quality check, you can manually shift to one or two bases to your right as well as to your left. And then you can take that particular sequence from here, anywhere. Like if there's a problem with the forward primer, what I can see here is this is the forward primer. Suppose it is not, passing our quality check. We can shift one or two bases to right as well as to left. I can go with T, A, T, T, C, A and till A, G, T. Then take that particular area, check for your complementarity. Same you can do with reverse also. But for reverse, what we do? Yes. When you're going for reverse, you need to go for complementarity. Complement strand. Okay? You're getting several bands. Okay. That, okay. First, you need to check also where your primer is going to bind in your sequence. You can do that also by clicking on blast. You can just click on blast and you can see that on which area your primer is going to bind. Okay, with that you can actually see if multiple sites are there, you are definitely going to get multiple bands. Okay, that is why we go for specific things, specific number of bases.
Okay, I think she has really beautifully explained how to design primer. Follow this. In the real-time amplification process, you never know what and all going to come. So many unpredictable things is likely to happen there. In any case, you have to standardize, right? Standardization not only for the primer but also for the primer PCR conditions. One thing I just wanted to highlight, TM value is not equal to annealing temperature. Please write it down in your notebook. TM value, what is seen on the screen, is not equal to annealing temperature. Okay? Annealing temperature is TA opt. TA opt. Temperature, annealing temperature, that's written TA. Opt means optimum annealing temperature. TA opt. How to calculate TA opt? Or it is an arbitrary reading or number? No. There are guidelines. Now the question is how to calculate TA opt. What is TA opt? TA opt is not equal to TM value. Clear? What is seen there is a TM value. How to calculate TM value? Please Google it out. Or OligoCalc can also guide you automatically. Just feed the primer sequence, it will give you what is a TM value. But nowhere you will find TA opt. Right? You have to calculate it. So there is a formula. The formula is a right-click formula. RYCHLIK. Right-click formula. What is this formula? A right-click formula. This formula exploits two parameters. One is TM value and another one is the length of the primer and also length of the product. Is it clear to all of you? TA opt equal to TM value of the product multiplied by 0.7 plus TM value of the primer multiplied by 0.3. Minus 14.9. I repeat, TA opt equal to 0.7 into TM value of the product, 0.7 into TM value of the product plus 0.3 into TM value of the primer, the whole thing minus 14.9. One of you please stand up and tell the formula. Anyone?
TM value of product into 0.7 plus TM value of primer into 0.3 whole minus 14.9.
TM value of the product multiply by 0.7 bracket plus TM value of the primer multiply by 0.3 bracket closed minus 14.9. Apply this formula, convert your TM value into TA opt, and that TA opt could be somewhat nearest annealing temperature of your primer. The beauty of this formula is taking into account not only the primer sequences but also the product sequences. Remember, product sequence excluding the primers. Right? Sometimes don't make a confusion here. When you retrieve the sequence from primer 3 plus, you have to be careful. Is it clear? Is it clear to all of you? Product sequence is in your hand. Primer the machine has given to you. Annealing temperature you derive from the oligocalc. So all parameters are there. So you have to simply apply those figures there. TA opt is calculated. Sometimes what happens, this TA opt may not work. Possible. Then what you do, you go for a gradient PCR, upper side 4 degrees, downside 4 degrees. I am sure one of them will work, provided the primer is okay. I think this is missed from her side, but this is one addition to the whole story. Okay. Any doubts? Separately you have to calculate. You have to calculate for each and every primer. Margin of 2% or 5% is okay. I am sure the value will be almost same. You won't get exactly the same figure deriving it. It will be one of the primers you may get, let us say 54.3. Another primer you may get 59. It doesn't matter. It will work fine. Alright. You just calculate whatever you design now, and you just calculate the TA opt applying this formula. Okay, using the TM value of those primers and product retrieved from the oligocalc. And TM value can be calculated using variety of online programs. This is not the only one. The oligocalc. There are so many are there. Try it out. Should not be a problem. Yeah. Any more doubts? Please continue.
Thank you, sir. I guess with this we have completed our primer designing session. Sorry? For RT-PCR, actually the process is, I generally go for IDT. It's an online available software. You can use IDT to design those primers. I generally go for IDT rather than primer 3 plus for qPCR because it is very apt. And what you can do is design your primers in IDT and give those for synthesis to IDT itself. So that is like, it is going to be helpful for you as well as the person who is going to synthesize them. No, no, no. You should pass all those quality checks before. No, you are saying that your sequence is self-complementary and your annealing temperature is good. It's better you pass that test properly. Acha. If any of the three parameters you're getting some value na rather than none here like what we are getting, it's better you go for the next set of primers rather than following with that set.
How to go for a degenerate trend?
Sorry, sir.
How to design a degenerate trend?
That I don't know, sir. You can tell. You can tell. Degenerate primers. You can tell, sir. No, it's going to be helpful for us also, the ones who don't know. I guess we are going to break for tea break and then we can go for the phylogenetic analysis. IRMM. You can use this software also to make your phylogeny. The format used for the ITOL is everyone here? Should I start? Okay, yeah. Is NAVIC, Philo, and some other formats are there. You cannot directly use your FASTA format or your TXT format for ITOL. Is everyone here? Okay, I'll start again. You enter FASTA to NAVIC in Google, then you will get this page and you click on format conversion phylogeny.fr by LIRMM. FASTA to NAVIC. NAVIC is the format which you need for ITOL. You have your FASTA files, right? You need NAVIC format for ITOL. Does anyone know or having any confusion why I am doing this? I've already explained though. ITOL needs a proper phylogenetic tree information. Like how much is the distance between them? It needs that data. Then only you can prepare the tree in that. So for that you need a particular format. That is NAVIC. Some other formats are also there, but I find this very easy to do. Okay. Everyone is here? Good. Then you click on phylogeny analysis. Go on that option, one click. As you can see, what is it is going to do? It is going to take your FASTA file, which is having your sequences. 14 sequences are there. Okay, what are for those 14 sequences? Though each sequence has at least 9 genes concatenated together. Okay, so that is not just one single gene, that is 9 genes concatenated together. Okay, so that is going to align those files using muscle, then it's going to do curation using G blocks, phylogeny using file M, L, and then redyne for tree. Okay, now you have two files with you, L15 and PPA1, I guess. You can use any of the two files, that's optional for you. Only one. I said optional means you have two, only one you are going to do.
One of them you provide.
Select your file. Just click on L15 or PPA1, it is going to upload that file. Any one of them, not both of them. Are we all together? Yeah. Then click on submit. See, it is going to show you how it is proceeding. First it is going to align those files using muscle. Now curation is going on. I guess all you know now what is curation. What is curation? Can anyone explain? Just 2 or 3 points. Curation means you are going to get a proper quality sequence. Now it is going for phylogeny.
This is an automatic. It's doing step by step and logic.
Now tree formation.
See there, extension already there, followed by step by step.
You can see a phylogenetic tree here. Is it visible in your laptops also? Good. Okay, this is software can also make your phylogenetic tree. Yes, sir, they are here. So, this software produces your dendrogram also. Phylogenetic tree analysis, you can do it here itself also. For iTool, now I am going to download the data of this phylogenetic tree in the Newick format. So, just scroll down. You can see rooted tree in Newick format. Download this file. The save as type should be tree file. Don't use any other extension here. Okay, just save it as it is. Okay. Just scroll down. You will see rooted tree in Newick format. Right click on it. Right click. Save link as or save address as. Okay. Don't use any extension to save this file like how we do .fast or .txt, nothing. Just keep it as such. Okay. You can name it according to you if you want. And it is downloaded.
Anyone?
All together? Okay, good. Okay. It's okay, sir. I'll wait. By that time, you can open iTool in next tab. Are we all here? Everyone here? Good. Now, you have opened your iTool next tab or new tab, I guess. Everyone following? Okay. Click on upload. I guess we are familiar with this page. Now you choose that file, the one which you have downloaded just now. And upload it. I guess we all are getting this tree now. You can now roam around the site all and do all the things like color, using nodes. You can get branch length also from here. Bootstrap also. So here so many options are there. However your experiment or however way you want to design it, you can design this tree. Nodes, internodes, depiction, everything is possible. Okay?
So here, according to your requirement, you can design your planting system.
I would like to specify design rather than phylogenetic tree analysis. No, design. Analysis you are going to do using your R or the other platform which I showed you earlier, before this I told.
Here I'm going to show you that I don't require some specific format. How to upload that specific format, how to convert it, and how to convert it. Just
Okay. Has anyone, I guess everyone has downloaded those software which I asked you to download, right? Okay, nice. I guess you can use only Mega. Okay. Okay, then I will tell about Mega only. There are many other ways you can do phylogenetic analysis. One is this. Second one is through CLC, sequence viewer, which I asked you to download. And the third one is Mega. Okay, if everyone has downloaded Mega, then I will tell about Mega only.
how many installed Mega?
I guess everyone. Okay. Mega is a very commonly used software for phylogenetic analysis for dendrogram preparations. So this software can also do alignment for you. So what we have right now, we just have some sequences in FASTA file. First, we need to align them. Okay? For that, what we are going to do, You click on align. I guess everyone has opened their Mega, right? Then you open Mega first. Sorry, sir. It's going to work, sir. It's going to work. Everyone here? Shall I proceed? Sir? Okay, good. Then you click on align here, this small tab. Click on edit/build alignment. Now, what we are going to do? We are going to retrieve sequences from a file. So, default, it is already there. So, you are just going to click OK. Then select that file. When you are going to select, any of the two files which I have submitted you, I have given to you file L15 PPA1, any of the one, you can select any one of them. Yeah, I've just now changed the format. Initially it will come as FASTA files only. You select all. Okay, it's better then you convert that file into .fasta then. You guys know how to convert a file into .fasta? .txt file into .fasta. Just use the extension as .fasta while saving that file. Open that txt file and do it. You can see here type is text document. Open this file. Go to file, save as, I hope it does, write .fasta. Save it. It will something like this you will get. To verify if it is properly converted into FASTA format, you check the type of that document. It should be FASTA file, not text document. Open that file, save that file as a title .fasta. You just type it. I hope everyone is here. I will repeat. Open file, save as that file name FASTA, and then save it. And you recheck whether that file which you saved is having a type as FASTA file. It should look like this. The type should look like this, FASTA file. Everyone? Okay, shall I proceed, sir? Everyone has done? Okay. You go back to your mega. Now repeat, align, edit build alignment. Click on OK. Select that FASTA file. It should start the progress. It is going to take its sweet time, so just let it proceed. Coming in. I'm doing it again, you can follow it. Just go to mega. Go to mega, align tab, edit build alignment. Okay. Select the file. You guys got it? Okay. Now, what this file this is not the curated alignment file. Now you're going to use cluster W for alignment of these files. This is not the alignment file. Okay? Go to alignment. Two options are there: align by muscle, align by cluster W. Here, I will, because muscle we have already used, right? So I'm going to use cluster W here. You select all. Just click OK. It is going to select all the sequences. Now, you can see it is giving some options here. Pairwise alignment. In that, you have gap penalty, how much you want in opening as well as in extension. For multiple alignment, how much, the same two parameters. Okay. You just click on OK. I'm going to go with the default properties. It is going to do both for you, pairwise as well as multiple alignment. This is the final thing. I hope everyone is following. Anyone stuck behind? Okay, now you have this file. It is your alignment file. Now we can save this file if you want. Okay, before saving, let me highlight some points here. You can see some star mark here, right? What are these star marks? The star mark is just the position where all the bases in every sequence are similar. Okay, you can see that so much dissimilarity is there, although they all are Microbacterium. Okay, and it is not whole genome. It is like some 9 genes from Microbacterium oliverans were selected and then concatenated together. Okay, those same genes are present in all of these other species also. So difference in genes is also there. That's why you can also use that gene to do your differentiation between the two species. Okay. For saving, you go to data, export alignment, mega format. You have to give input title of the data also. You can give the same. Now we will ask you, do you need protein coding nucleotide sequence data also? That means it can convert your nucleotide sequence into protein sequence also. So you can just click on yes, no problem. We want as much data as possible. Are we guys together? Okay. So now what we have? We have our alignment file. What is the next step? We are going to do phylogenetic tree preparation. Come back to your home. Just minimize that. You will come back to your home page. Okay? We all are here. Okay. Now click on phylogeny. Now it will give you multiple options. Maximum likelihood tree if you want, neighbor joining tree if you want, minimum evolution tree if you want, maximum parsimony tree is also there. So according to what is the requirement, you can select. Here I am going to do with the most commonly used one, maximum likelihood tree. Okay. Now select that alignment file. See, so many options here. And you need to note these downs, because when you are going to write a paper, you need to give these details, like which model you are using for the tree preparation. Everyone is here? Just take a print screen, or if you don't want to, take a print screen. Okay. You can see the statistical method used here is maximum likelihood. Okay. Then the model used is Temurani model. There are many other options available here. The most commonly used is Temurani model, but some people have seen papers using Kimura also. But it depends what you want. Okay. Heuristic method used here is NNI, nearest neighbor interchange. Another thing was also there. Okay. Everyone here, click on OK. Now you will get your I guess this tree is working good for me because my target here was L15 and it is showing similarity with oliverans only. So I guess my genes are specific for oliverans. It's good. All are following? You can read this tree. Okay? There are multiple options here also. Let's circle if you want. See? The traditional rectangular if you want, the one which we actually, it actually gives as a default. You can use straight also. Just, you know, go through this May guide. It is also very nice tool. Are we good? So this was the second option, but not, this is for, you know, not for your metagenomics, because if you are going to use that here, it is going to take overnight to prepare tree or you do alignment for that purpose. Okay, this is for short sequences only. Okay, has anyone used CLC before? CLC sequence viewer before? Anyone? My team, I know they have used. Okay, CLC, there are two type of platforms. Okay, one is sequence viewer and the second one is workbench. Workbench you can use for your transcriptome as well as metagenome as well as whole genome sequence analysis. But the problem is you need to get a license for that. You can easily download sequence viewer. Okay, that sequence viewer you can use for alignment as well as your phylogenetic tree preparation. So that is the thing with the CLC. And you can use FASTA format directly there. Like here we have converted TXT to FASTA format, right? There you can use direct TXT also, no conversion needed. Do you want me to show you? You can also download it by that time. It is online, it is not that much heavy to download. this is how a CLC sequence viewer interface looks like. I guess we have time, so you can download it. It's better you download it. You learn this also. CLC Sequence Viewer 8. If one more version is available, you can use that also. The process is same. Everyone here is downloading, right? Javed sir, has everyone downloaded? Can you please tell? Downloaded, right? It's not that big, you can download it with your cellular data also, no problem. Okay, now I'm proceeding. So, what is the first step in CLC? You need to import your file into the CLC panel. So, for that, you click on import. Select the file. See, I'm using txt file here. Any one file, L15, PPA1. If you want to do both, import it. Any file you can use, txt file, faster file. You can create a folder also in which you want to import your files. So here I'm going to create a folder also. See, a folder is created here. Select the folder, finish it. Can you say this is the panel side of your interface? Here you can locate all the files which are there in your CLC workstation. Okay? Can you see my file here? Can you see your file in your laptops? Shall I repeat? Okay. Go to import. Select your file. You can select FASTA, you can select .txt, no problem. Okay? Then you just click next. It will ask you in which folder you want to copy. Okay? You can give a new folder name also if you want. Then you just click on finish. imported your file? Don't delete your file. I'm deleting this file because I copied it twice. Okay. Now your file is imported in your workstation. Next you go for toolbox. See how many options it's giving you. Alignment entries, general sequence analysis, nucleotide analysis, convert your DNA to RNA, RNA to DNA, reverse complement sequence analysis. See? And what we are going to do? We are going to create an alignment. So go for create alignment. I hope everyone is here. If your file is already visible in the selected element region, no problem. I went back so that I can tell you how to shift your file. Everyone here? Okay, then select your file and ask it to move here. Now your file will move to the selected element region. Your file should be visible in this area, selected element region. You can create alignment of multiple files also. So if you have two files of same organism, of course, because the two files which I gave you are of different organisms, so don't mix them up, otherwise you will get confused. Yeah. This is what I am doing. You want me to repeat? Okay. Go to toolbox, alignment entries, create alignment. My file is already here. Following? Okay. Then you click on next. See, it is also showing some set of parameters. Gap open cost, what it is, you read it. And gap extension cost, how much. I will opt for very accuracy alignment here, which is going to be slow, but okay, we don't have that much of sequence length, so that is not an issue here. Click next here. Ask it to save your file. Click on open log. What do you mean by open log? It will tell you sequentially what is going on within your file, okay, while it is doing the alignment. Click on next. Now it will ask you, where do you want to save your file? You can select the folder. For me, it is going to be MLSA here because I created a folder for that. I guess I'm not going that fast, right? Okay, just tell me, huh? All here? Then ask it to do the job. See, this is the log. What it is showing? It was showing actually aligning 10 sequences. Okay? What is the message here? Done. Alignment finished. See, your file is here in the folder which you selected. Can everyone look at his or her file here? Right? You can open this file. See the alignment. For every base, a particular color is there, color coding is there. Okay, like for T it is green, for G it is yellow, for C it is blue, and I guess for A it is red. So color coding alignment is there. You see, if gaps are there, it is showing you how much gap is also there. It is going to show everything there. I generally prefer this CLC for alignment purpose. When you will start using all these softwares now, you will come back here. I'm very much sure about it. Just scroll down, see the file. Can you see here? When all the sequences are present and they are, similar at that particular position, that base is similar at that particular position, it's going to show you full bar here. So that is like an indicator for you when you have so much sequences. Just rather than going for sequences, just focus yourself on that bar and then you will see where mismatch is there, at what base it is happening. You can do that. Okay. CLC you can very good, it's a very good platform. You can use it for curation part also. You know what is sequence curation? Normal sequence curation. You check base by base that if the quality of that particular base is good or not. Okay, I guess I have given you some softwares for that also. Finch TV you can use if you have your AB1 files. Are you guys familiar with what I'm talking? Good. Getting? If not, then I'll tell you. Okay? Okay. Now you have your alignment file. Next is tree preparation. Same, go to toolbox, alignment and trees, create trees. Okay, as I've already opened my file here, it is automatically showing my file in the element box. I hope there is no confusion. Go to toolbox, alignment and trees, and then tree. Also, it is going to show you some parameters like neighbor joining. I don't know what is UPGMA, I really don't know. I'm going to go with the default one, neighbor joining, which is mostly used, okay? See, these two are very important, Jukes, Cantor, Kimura, okay? You need to read why these heuristic methods are used. Okay. Just click on next. I'm going to save this, so I'm asking it to save my file. I want it to open my log. Select the folder where you want to save the file. Same process, very easy. Click on finish. Everyone following? Open your alignment tree file. Yeah, here you have it. You have your tree here? Can you locate this area? Just click on any one of them. You will see all the parameters used. See which algorithm is used, which distance measure parameter they have used, bootstrap how much it is doing on. That option is not there. You cannot, make any other type of phylogenetic tree here. Sorry? Tree layout is there? Okay. Yeah, right. You can do all the, yeah, it is there, it's there. Sorry, yeah, that option is there. I've used the older version. Okay, label setting is also there. Yeah, bootstrap is also there. Yeah. Everything is there. Same as Mega now. Sorry, sir? Yes, sir, it will give that NAVIC format. Yes, see how many formats are there to save it. One NAVIC format is also here. You can use CLC also. No, sir, this NAVIC format you can use for ITOL also. Yeah. Yeah, it will open in mega file. Yes. Yeah. So you can take data of your phylogeny from here also and then upload it in ITOL and use it. You can play with that now. No one is stuck behind, huh? Everyone is following what is happening here, right? that is the end of this session. If any queries there, I'm here.
You can tell online. We have seen two major practicals. The first one is primer designing. I think you might have learned the details of primer designing and how to check the primer quality, how to calculate TA opt using right-click formula. That is one of the very important practicals all of you would be using certainly in your PhD thesis or maybe beyond that, any projects, whatever you are handling. There is no doubt, right? And this primer designing also, there is number of online programs are there. The one what she shared is only primer plus, primer 3 plus. IDT, the company launched their own program for real-time primers. I think end of the day, ultimately you have to practice it. If you don't practice, you will forget it faster than the time it took for learning. That is for sure, right? So end of the day, for practice also, you don't have to wait for your own data coming to your desk, because that may take a lot of time. The best way forward is in our own area of research. Somewhere somebody might have already done it, right? Isn't it? The information might be there related to the pathogen or microbe, whatever you are handling. And get into those data, retrieve the data sets from online resources, and try to make some sort of analysis. For example, primer designing, if you want to design a primer for a detection or a copy number estimation of a particular gene in an organism or detection of a pathogen. She nicely explained, you get into the whole genome data, use that whole genome data as an input to design primers. the point is why whole genome data? Because whole genome data, it serves two important purposes. Number one, identity of the organism. Most often, without establishing the species identity, nobody would have ventured into the whole genome sequence. So that way, you have a bit of authenticity in the data, especially from the taxonomic point of view, right? Number two, the data quality. A poor quality data, the database would not have allowed them to even publish. So the data quality must be of accepted standard, right? So years ago, what is accepted standard? I think we had a lot of discussion in the last week about draft genome and complete genome. What is draft genome and what is complete genome? Draft genome is a genome where you present your data in the form of certain number of contexts. It need not be a complete genome, and that means there is always some gaps in the genome. And there is a margin of error as well. Somewhere I read 1 base pair error in 10,000 bases. That is a standard. That means that's a very good quality sequence. One error in 10,000 bases is something amazing. So this data is good enough for all of us to use in our own area of research. Complete genome is something which is very, very challenging, and many places people are still struggling to complete the genome for various reasons. Repeat elements, difficult regions to sequence, all those things will be there, and the genome is not complete. So what people do, they publish a draft genome, but somewhere the data should be uploaded and it is accepted at international level, and the consensus. We will encourage the draft genome populating the databases. So for these two reasons, less error, correct taxonomical identity, that gives you some confidence in using the data for your own purpose. Retrieve the data from the whole genome and try to design primers using the options what she shared already, designing part, checking part or validation part, then the formula what I shared here, right click formula, 0.7 into TM value of product plus 0.3 into TM value of primer minus 14.9, that gives you somewhat closer to the annealing temperature. Then you play with that, keep it as a midpoint, and on upper side 4, downside 4, go for a gradient and optimize your primer amplification, your amplification conditions. I'm sure you have a lot of data already generated in your own organisms, whatever you are handling. You practice that. That practice keeps you a lot of confidence. And otherwise, I'm sure as the day progresses, you get lost in your own activities. Very little scope for to sustain your interest. So all kind of things are likely to come. Unless and until you have something officially assigned to you, you will not be able to do that. I am sure you will not do also. So the best thing is you try to sustain that interest, and you analyze the data, secondary data analysis, and you never know, you can even go to a publication level also. And some students have done it. They never sequenced it. They only handled the secondary data, brought out an information which the original sequencing team has never brought out. A lot of scope is there for this activity, lot of scope. What I am trying to tell you, you don't have to really invest your time. The sample preparation and all, whatever I told, redundant, no need. You have already the data uploaded somewhere. You retrieve them and try to analyze an area which nobody has done it. One example I can tell, the fungal genome. Fungal genome is loaded with the transposable elements. I'm not seeing too many papers coming in the journals. That means people are not showing any interest. This is one area, right? I'm sure in the same way, bacterial genome also. You can get into the bacterial genome, try to analyze the NEO team. They clearly told NRPS gene clusters. You can analyze that and come out with some kind of gene clusters coding for some novel antibiotic which nobody has explored option. So what I'm trying, at end of the day, you have to create a platform for yourself to use all these tools so that you come out with something that might get you a publication also. There is always a scope. Okay, do that. That was all about the primer designing and validation part. And afternoon, we had one more practical, very important practical, molecular phylogeny. Before coming to this course, I'm sure most of you would not have heard about ITOL. Maybe one or two might have heard, but majority of you might not have heard about ITOL. So you learned it now, how to use it. So I see this as a positive sign in terms of the objectives what we had in our mind, teaching something which you never know before. So I told you, and she also went into other programs like CLC, genomics, sequence viewer, all those things. And what you are having right now in your desktop is a free version. And the CLC has got its own original version, priced at around 3 to 4 lakh rupees. If you are spending that much money, it's worth spending if you want to stick on to this subject forever. And certainly it is going to support you, because we did the same thing in 2016, and we don't depend on the companies for data analysis. We do the data analysis in-house. I want that to happen in you as well, because very often the company's analysis is a standard pipeline they use. Many times you may not be able to get the biological question you raised in your project answered from that data. And if you want to know the answer for those biological questions, if you approach the industry, they will again ask you extra money, because they always say the standard output is the one which we can always give. Anything extra is priced separately, because they count in terms of hours spent on the computers for charging. So our own experience and our own the thought process, what I am suggesting to you, sequencing data the day it is generated, you ensure that it is coming to you as well. The industry can send the sample to their own people. I'm sure some industries are having excellent bioinformatics support. And I don't say that we can do a better job, they can do a better job. Sometimes some of the genomes, we have a very good experience with industry. They have done an excellent sequencing analysis also. And sometimes we also do a better job. So you get two sets of data delivered to you, your own data, analyzed data, another one is coming from the industry as an agreement. So you take the best one which is needed for you. That should be the strategy forward. Okay. Molecular phylogeny is something all of us do for a variety of purposes. I think we have given you hands-on training on that. Tomorrow we have a follow-up theory of this molecular phylogeny, because I'm sure a lot more need to be conveyed to you in terms of molecular phylogeny, especially what should be the tree for what kind of data. It's not that every molecular phylogenetic tree is recommended for every set of data. It all decided by the objective of your work, the quality of data, whatever you have. And these are all some of the things you keep in your mind. Tomorrow we'll have that lecture, molecular phylogeny lecture, scheduled at 2 o'clock. We'll listen to that. And I think with today's practical, with the practicals what we had in the last week, and tomorrow's molecular phylogeny theory, I think you will be very close to understanding the whole game of this molecular phylogenetic tree construction. I think that's all today I just wanted to convey. And if you have any specific requirement on this area, metagenome data analysis, barcoding analysis, single gene based molecular phylogeny, we have 2 more days to go into the program, and if you in the program, you can try to address that. And series of lectures are planned tomorrow also, day after tomorrow also. Let us wait and watch how the course moves to the last day. Okay. Thank you. Yeah.